All right, let's find the area of this polar curve. And so if we're trying to find this area, we could do our fancy polar formula to find the area. But I want to do a quick derivation of this formula so you can understand where the intuition comes from. Your calculus teacher might have given you the formula and just said here, but I want to show a quick derivation of it. So we have our little circle here, and then we can kind of put this in some calculus terms later. If this circle has a radius of r and with a angle of theta, and we want to find this area of the sector, we know that whole area of the circle, the whole area of the circle is pi r squared. From middle school geometry, the area of a circle is pi r squared. Now, if we wanted to find the area of a certain part of it, we know that this area is going to be a fraction of the entire area. And so we can imagine going around this circumference here 2 pi times, because the you go around a circle 2 pi, that is the circumference. And so this angle theta is going to be a fraction of the whole circumference. And so then we can do some cancellations here. We can cancel out these pi's, and we get the familiar of 1/2 is pulling the 2 out front of r squared times theta. Now, if we have a function of r with respect to theta, and, and theta is changing, we can do this with a integral, just integrating from some theta 1 to theta 2. So I'll call those this theta 1 and theta 2. We'll pull the 1/2 out the integral. We have r of theta, because this is a function of theta, squared with respect to theta. Because if we had some generic function, I'll enlarge the picture on the right. When we wanted to find the area of this, we could start by just saying, let's find the area of this using our our formula like this, and we can imagine this is just some tiny d theta. And then we could add up these tiny little angles, these areas that as we go around the polar curve. Okay, so now that we have the idea of behind the formula, let's go ahead and write out this integral. So we know to pull out our half, and we have an integral. But what are our theta bounds? So we can see from the picture that it goes from, this is angle 0, then it goes, oh, it goes from angle 0 all the way around to 2 pi. So in this example, we are going to say this is 2 pi. You could also work it with the idea of symmetry. We know that we can just go from instead to from 0 to pi, and this area is the same as this area. And then we could just multiply it by 2 at that point. but I will leave it at the 2 pi. And so our next step is to say r of theta d theta. And so we do 1 plus cosine theta. This is the quantity is squared d theta. And then you could type this into your calculator and you would get 4.712 about approximately. Right. We have another really bad drawing, but it's okay. So we want to find this area that is shaded in red, and we have our function of r with respect to theta. So the first thing you want to notice is that this is supposed to intersect at the origin. And so we want to find these angles so we can just integrate over these from theta 1, that looks like a Q, to theta 2. So the best way to go about doing that is setting r equal to 0. So we're going to say 3 minus 6 sine theta is equal to 0. Adding 6 sine theta to both sides, we get 3 is equal to 6 sine theta. And then we're going to divide both sides by 6 and get 1/2 is equal to sine theta. 1/2 is equal to sine theta. And when is sine theta equal to 1/2? That is when we have a reference angle of pi over 6. Uh, that is something you just kind of need to know, but I will show you a little handy trick that I learned in maybe the ninth or 10th grade. So if we have sine of theta and we have theta. And so we're gonna go in order from smallest to largest of our uh, key angles. So we have 0, we have pi by 6, pi by 4, pi by 3, and pi by 2. And then the rest we can do this with the reference angles. Because we are going from this part up to here. The rest we can work out with reference angles. And so the trick I learned was then you do the square root of, we'll do this in yellow. So you say square root of 0 over 2, square root 1 over 2, square root 2 over 2, square root 3 over 2, and square root 4 over 2. And as you do more of these, you just kind of memorize them. And so you won't think of it as square root 0 over 2. You just know that that's actually just 0 or 1/2. Uh, these two, you basically say the same, and this one will be 2. Because these square roots are kind of weird, and if you don't want to draw the reference triangles, you can kind of just imagine them in this order. And then cosine theta, we'll just go backwards. I don't know where S. Cosine theta starts at square root 4 over 2 and works backwards. Just a handy little trick if you can't memorize some of your sine identities. But we see that pi by 6 is the reference angle we're looking for. So we have this angle right here is pi by 6. So we're going to say pi by 6. And the other one will also have a reference angle of pi over 6, but it appears to be in the second quadrant. So the reference angle is basically the angle from the x-axis that has a specific angle. So we want to be in the second quadrant, but have an angle of pi over 6 from the x-axis upwards. So we know that this full angle is pi, and so the other one is pi minus pi by 6, if you want to think about it like that. And so I'll do some simplifying here to get the second reference angle. So we know that it is pi minus pi by 6. So minus pi by 6. We want to end the second quadrant. So we're going to subtract to pull it up that way. And so I'm going to multiply the numerator and denominator of this by 6. So we can add these like terms. So this is going to be 5 pi by 6. 5 pi over 6. And those are our bounds of integration. And so now we can integrate this. And usually for the non-calculator questions, they're going to say, write this integral. So we're going from pi by 6 to 5 pi by 6. So if this is a non-calculator question, this is where you would stop. And if this was a calculator question, you'd substitute this into the calculator. And so this is our r, and so we say 3 minus 6 sine theta, and the entire quantity needs to be squared, and we are integrating with respect to theta. And so this is approximately 4.8916. So what if we wanted to find the area between two polar curves? When you have a question like this, you need to be very intentional about what you are doing. We have our two R1 and R2s here. And the first thing I'm going to do is I'm going to see that they intersect. And so these are very important points because we know when we're going to integrate, we want to first go find the area from here to here bounded by this R2 curve. And then we want to go find the area from here to the next intersection angle of the R1 curve. Because you're adding up these areas. And what I might even consider doing is starting down here. So I can just have two integrals and not three. So I would add up the area from here, this point of intersection. We're going to go around, add up this area until we get to here. This is all bounded by the R2 curve. And then we're going to, I'll do this in, what's the color I haven't used? I guess I'll do this one in yellow. So then we will go from here, and this area is bounded by the R1 curve. So we have to go and add up this area. And do not be fooled, these are two different angles when we are doing this. Because we're starting from the negative direction here, and then we're going to go around. So it's still going to add up to 2 pi, but we start from a negative value and don't go all the way back to 2 pi. So let's set these equal to each other to find these points of intersection. So we have 5 minus 3 sine theta is going to be equal to 5 minus 3 cosine theta. So if I subtract 5 from both sides, we get rid of the 5, and then we divide both sides by -3, and we are left with sine, not 3, sine theta equals cosine theta. And if we really wanted, we can divide both sides by cosine theta. And so dividing sine by cosine, we get tangent theta. And dividing cosine theta by cosine theta, we get 1. So tangent theta is equal to 1. When is tangent theta equal to 1? That is going to be at a reference angle of pi by 4. Pi, pi by 4. Pi by 4. If I can write. And that's because sine of pi by 4 is square root 2 over 2. And cosine of pi by 4 is square root 2 over 2. Dividing square root 2 by 2 by itself, we get 1. So when does tangent theta equal 1? It's going to be a reference angle of pi by 4. And so that's this angle in the first quadrant. But we also want a reference angle in the third quadrant. Still going to be positive, and so we're going to add pi by 4 to pi. So that's going to be 5 pi by 4. So those are our angles. Now we have our angles, we can do our integrals. So we're going to pull up the half, and we're going to start with this curve, like I said before. So this angle, if we go from the negative direction, is actually negative 3 pi by 4. So I will also kind of notate this as negative 3 pi by 4. Because if we go around this way, this is 3/4 of a pi. But we're going backwards, so it's negative. So I'm going to say negative 3 pi by 4. And then they intersect at pi by 4. And what curve is being bound here that we're taking the area of? We need this area right here. That is bounded by the R2 curve. So the function we're going to put in there is our R2 function. 5 minus 3 cosine, I don't know what that is, cos theta. The entire quantity is going to be squared, and this is going to be integrated with respect to d theta. What about finding this next area? Well, we have to pull out our 1/2 again, and then we're going to integrate. And this time we're going from pi by 4 to 5 pi by 4. This angle all the way around to this angle. Pi by 4 to 5 pi by 4. And what area are we looking at that is bounded here? That is the R1 curve, the 5 minus 3 sine theta curve. So we're going to have that be the quantity of 5 minus 3 sine. What did I have it? Let's try that again. 3 sine theta d theta d theta. And then if we enter these two integrals into the calculator and add them together, we get 50.2505. Thank you.